So we finally made it to this part of the course where a lot of you have been asking about Lagrangian dual function. I believe at this point of the course we're ready to introduce what the Lagrangian function and its dual mean with respect to an optimization problem. We'll be discussing about the Lagrangian duality, stating some lower bounds on the optimal value of any optimization problem. We'll be giving some examples as well as MATLAB applications to view some lower bounds on the optimal solution. Examples include the two-way partitioning problem, an LP standard form problem, and a least square problem. In the last part of this course, we'll see a direct relationship between the dual function and the conjugate function of the cost. We'll be giving some direct examples such as the equality constraint norm minimization and the entropy maximization problem. So without further ado, let's get started. So the first topic we're going to talk about is the Lagrangian function. So given an optimization problem in standard form, so our vector x is an Rn with m inequality constraints and p equality constraints. The cost is f0 of x. The domain of this problem is the intersection of all domains of the functions f0, fi, and hi, which we assume is not empty. So this is one thing, and the other thing we will denote throughout this lecture and throughout this course p star to be the optimal value. So it's f0 of x star, where x star is the optimal solution of the problem. And one thing to notice is that we're tackling optimization problem in standard form. So in general, we do not assume that the problem is convex. So this problem need not be convex. So it's any optimization problem. So what is Lagrangian function or the Lagrangian duality in general? So Lagrangian duality is to take the constraints in this problem that are fi of x negative and hi of x equal to 0 and augment it to the objective function as a linear combination or a weighted sum of constraints. That is, we define the Lagrangian function L of x, where x is a vector, lambda is a vector, and nu is another vector, to be the cost plus a linear combination, so weighted sum of lambda I fi of x, where I goes from 1 to m, plus a linear combination of nu I hi, where L is clearly a function takes three vectors, each of size, x is of size n, lambda is of size m, and nu is of size p. Why is that? We have m lambda i's and p nu i's, and it returns a real number. So we're just mapping all this to the real space. And the domain of L will be the domain of the function right here, d. So this is in x, and in lambda it's just rm, so times rm, and in nu it's rp, so times rp. We usually refer to lambda i's and nu i's as Lagrangian multipliers. Now the vectors lambda and nu variables, or are called the dual Lagrangian multiplier vectors. So those we could refer to as dual variables because we created those variables. We augmented the constraints. So yeah, that's about it on the Lagrangian function. So it's just a linear combination of all associated functions in the problem. Now let's move to another subtopic, that is the Lagrange dual function. So this L is referred to as the Lagrangian function, or simply the Lagrangian. The Lagrange dual function is something else. Okay. To be precise, it is the Lagrangian. You take the Lagrangian, L, x, lambda, nu, which we defined as f0 of x plus sum of lambda I fi and a sum of nu I hi. So you take this function and you consider the infimum over x, where x belongs to the domain of the function, right? So this will return a function in lambda and nu, which we will call g lambda and nu. So this guy, g, is referred to as the Lagrange dual function. You're looking at the lower bound of the Lagrangian function with respect to x, right? So you're omitting the variable of interest by taking the infimum over x. Now one might come and say, is this the optimal solution? Well, no. Given some conditions, which we will see later on in this course or this lecture, it turns out that yes, x could be optimal, but not always. And note that when L is unbounded below an x, then G is clearly minus infinity. So the case where if you happen to have G lambda of mu is equal to minus infinity, this means that L is unbounded below in x, right? Because you're trying to find a lower bound in L with respect to x. Well, if you hit minus infinity, then L is unbounded below in x. There's no x that returns a finite infimum. Another thing to note is that since the dual function is an infimum of a family of affine functions of lambda and mu, so note that L, the Lagrangian, is in fact affine in its duals, right? So it's affine in lambda and mu. It's simply just a linear combination of lambda I and mu I. They show in linear terms. So lambda I only shows once as lambda I fi plus something independent of lambda I, right? Likewise, mu I shows only once as mu I hi plus something else that is independent of mu I. That said, L is linear in lambda I, mu I. So hence it's affine in lambda and mu. Now since this is the case, since G lambda mu is an infimum of affine functions in lambda and mu, then G lambda mu is concave, even when the problem is not convex. So this is always true, regardless of the nature of the problem. Now let's look at something really important, which is an upper bound on G, the Lagrange dual function. It turns out that G lambda mu is upper bounded by the optimal value P star of the problem. So we can call this subtopic as the lower bound on P star, the optimal value. And why is that? It's because if we take a look at the Lagrangian function Lx lambda mu, which is f0 of x plus sum of lambda I fi plus sum of mu I hi. If we pick a feasible point, let's say our feasible point is x bar, so we plug x bar everywhere instead of x. Since x bar is feasible, and assuming that, we didn't say this before, but usually we're going to restrict all our lambda i's to be positive. So if that is our case, then since x bar is feasible, then fi x bar should be negative and hi x bar should be set to 0. Why? It's because they're feasible, so they should satisfy the constraints of the problem. That said, this guy is 0, and this guy is negative, since we know that all lambda i's are positive and all our fi of x bars are negative. Positive times negative is a negative, sum of negatives is a negative. That said, we've got f0 of x bar plus a negative. This means that my Lagrangian function is always upper bounded by f0 of x bar for any feasible x bar. This is true. So now if I come and take the infimum over all feasible points that are in the domain of the problem, so if I come and say in x and d L x lambda mu, this should be lower bounded by Lx bar lambda mu, which is in turn lower bounded by f0 of x bar. Now this guy is G lambda mu. This means that G lambda mu is less than 0 of x bar for any feasible x bar, right? So let x bar be the optimal solution, because the optimal solution is indeed a feasible point. So in particular, we get that G lambda mu is less than P star, because for x bar equal x star, this evaluates to P star, and hence this is true. Well, let's use a bit of MATLAB to visualize this bound. I'm going to create a main script where I'm going to define the lambda axis. So my point here is given a problem as such, f0 of x, and I'm going to, for simplicity, only consider one inequality constraint. So I'm going to be looking at this problem right here. So I'll minimize the function f0 of x, which is not necessarily convex, subject to a norm constraint. So x squared is less than 1, and x, we've got only one variable x. f0, we're going to consider the following form, which is x cubed plus 2x squared minus x plus 1. Let's see how this function for a while looks like. So minus space, minus 2, 2. Going to span an x from minus 2 to 2, and I'll take 1,000 points. And now I'll plot x cubed plus 2x squared minus x plus 1. As you can see, this is the function f0 of x, and we're only interested in this area right here, right? So this is my feasible set right here, minus 1 till 1. Those are the values of the function, right? Let's put take the y limits, and I'll hold on and I'll plot. So this is where we will be looking at. This is the constraint telling us look at this region right here. Now, let's go and create another function. Call it func1. So func1 is going to return a value, and it takes two inputs, the x and the Lagrangian multiplier L. So what is the Lagrangian of this function, of this problem? It's simply x lambda. We don't have a nu because we don't have equality constraints. So this is equal to f0 of x plus lambda 1, or lambda for simplicity, times x squared minus 1. Note that the f1 of x right here is x squared minus 1. It's here. Okay? So plugging the form of f0 of x, we get x cubed plus 2x squared minus x plus 1 plus lambda x squared minus 1. So I'm going to copy this function right here. So f is x cubed plus 2x squared minus x plus 1 plus L times x squared minus. Now I'm going to go back here and I'm going to define, I'm going to see this as a function of x only. So I'm going to look at my function as a function of x so that I could minimize only with respect to x. So at each L, I'm going to minimize with respect to x. So for that, I'm going to loop over values of L values, or L vowels. And right here, I'll define a set of values, line space. So we're going to restrict to positive Lagrangian multipliers. I'm going to look at the space of from 0 to 1, and I'll initialize G to be an empty vector. At each iteration, I'm going to increment the value of f min, okay? So at each iteration, we're looking at a minimum Lagrangian function with respect to x. I'm changing L, and at each L, I'm minimizing with respect to x. So that's another way of finding the Lagrangian dual function, G. Finally, I'll plot G. So run, and this is what we get. This is our G. Now let me just label the x-axis lambda. Does it work like this? Yes. This is our lambda, and my y-axis should be the G of lambda, right? Now, what is P star of the problem? If we open another figure 2, I'm going to plot, so I'm going to define x vowels to be from minus 2 till 2, and I'll take 1,000 points. I'll plot x with, define my main function, which is f naught, that is x cubed, is this part right here, right? Or this guy right here, right? So I'll copy paste it here. Don't forget the dots. This is pointwise exponentiation. And I'll just plot it. Problem. It should be x vowels right here. Don't forget that. Don't forget a CLF to clear the figure if it already exists. This is my function, and this is my P star right over here. Now, over this part. Now, why don't I just go and just limit function in a window minus 1 to 1. So if I go here and say min of f0 of x vowels, I get 0.8874. This is P star. I'm going to plot a dashed upper bound. X minus 1, x minus 2, and P star, P star. And there you go. You can see we've got a nice upper bound. It's upper bounded by P star. This is G of lambda. This is P star. We put a legend. There you go. Now we can change the values, really. Let's look at this window. Let's see what happens with the same minimum. Of course, this is not going to change much. Let's change the values right here. So if this is a 3, and if I go here and change this to a 3, run. Well, what is P star? 0.92. Still reserved. So this is also upper bounded as well, right? Now, if I change this to a 30, say I change this to a 30, the upper bound is now 0.99, right? Yes, 9917. Let's change the coefficient of x and run 0.8 something. As you can see, g lambda is always upper bounded by p star. That's the point of this MATLAB simulation. Now let's see some examples of Lagrangian dual function. So first going to consider the least square problem. So say I've got to minimize the norm of x subject to an affine constraint ax equal to b. The Lagrangian of this function, note that we don't have a lambda, it's a nu, because we don't have inequality constraints. So it's f0 of x plus, now I could write sum of nu I, and over here I could say, look at the ith component of ax minus b, right? So ax minus b is a vector equal to 0. Ax minus b is equal to 0. And this is my h of x, which is a vector. Now, if I look at the ith component, I could weigh it or multiply it with nu I. Another way of writing this is by saying it is nu transpose times ax minus b, right? The same thing. And another way of writing the norm of x is x transpose times x. Now, if we want to minimize or find the infimum with respect to x, all I have to do is take the gradient with respect to x of the Lagrangian. That is simply 2x plus a transpose nu. Set it to 0, you will get that x is minus half a transpose nu. Now, plugging x back into the Lagrangian, this is x, let's say 0. So g of lambda, which is what I'm looking for, is L of x 0 nu. It's not g of lambda, sorry, it's g of nu. We don't have a lambda. So plugging this back into the Lagrangian function, you will get 1 over 4 nu transpose a transpose nu, plus nu transpose n2 minus half a transpose nu minus b, right? Expanding, you will get, now this is a quarter times a term minus half times the same term. So you will get minus quarter mu transpose a transpose nu minus mu transpose b, right? Finally, this is your g. This is your Lagrangian dual function over here. This is an analytical expression of your Lagrangian dual. Let's see another example for LP problems in standard form. So we're minimizing a linear cost subject to an affine constraint with a positivity constraint on x. The Lagrangian, this time we've got a lambda due to this constraint, Lx lambda nu, that is f0 of x plus sum of lambda I fi plus the sum of nu I hi. So as we did previously over here, ax equal to b, which is written as ax minus b equal to 0. The sum is easily seen as an inner product, so that this term is likewise mu transpose times ax minus b, right? f0 of x is simply c transpose x, and our fi's over here are simply minus xi, because this is written as minus x negative. So we've got m or n constraints of the form minus xi is less than 0. So this is easily seen as sum of lambda I times minus xi, right? Which is, also written as lambda transpose times x with a negative due to this minus over here. So my Lagrangian is finally c transpose x minus lambda transpose x plus mu transpose ax minus b, right? Expanding, you will get c transpose x minus lambda transpose x plus mu transpose ax minus mu transpose b. Collecting all terms that depend on x, you will get c transpose minus lambda transpose plus mu transpose a times x minus mu transpose b, right? Now, Note that you can't derive here with respect to x because you will get a gradient independent of x. So that means that if you want to find the infimum with respect to x of the Lagrangian function, which is the Lagrangian dual function, right, which is what we're looking for, this guy, we've got two cases. If this vector right here is 0, so if C transpose or minus lambda transpose plus mu transpose A is equal to 0, that means simply your dual is just this term. So it's minus mu transpose B, right? It's independent of x. However, if this term is not 0, then you can always find an x that pulls this cost or this function downwards towards minus infinity. That means it is unbounded below. It's minus infinity. So one final example could be the two-way partitioning problem. So assume that we're minimizing quadratic cost x transpose wx subject to each xi square is equal to 1. And my xi's are either minus 1 or plus 1. Note that this is a discrete problem because our xi's belong to a discrete set, minus 1, 1. It's binary. And you can, just do a brute force search, an exhaustive search over all possible xi's, all combinations of vectors. So let's say my n here, the size of x vector. So I've got 3 x's, this small example. So all possible points are either minus 1, minus 1, minus 1, minus 1, minus 1, 1, and minus 1, 1, minus 1, and so on. You've got 2 to the power 3 combinations. So in general, you've got 2 to the power n points, and you could just exhaustively search for the minimum. That's not practical when n is large. The complexity of the problem is exponential, as you can see, and this is why this is called a two-way partitioning problem, because the solution is in fact just going to turn out to be minus 1, minus 1, 1, minus 1. It's just choices of minus 1 and 1. So you're basically partitioning the set of indices 1 to n as two sets. One set where the indices correspond to xi being minus 1, and the other set of indices is when xi is plus 1. So this is the two-way partition. So let's write down the Lagrangian of this problem. So I don't have a lambda because I don't have inequality constraints, so it's a mu. My f0 of x is x transpose wx, and my mu is plus sum over mu I times the ith equality constraint equal to 0. So it's xi squared minus 1 is equal to 0. That said, I could expand this term as two summations, mu I xi squared minus sum of mu I, right? Now in vector form, we could write the second summation as x transpose vx, where V is a diagonal matrix composed of the Lagrangian multipliers v1, v2, down to vn, right? You can verify that x transpose times v times x is nothing other than this summation. And the last summation is nothing other than a vector denoted by 1 transpose v, where 1, the vector 1, is a vector of all 1's, okay? You can also verify that this term is in fact the summation. Now let's collect terms that depend on x, get x transpose into w plus v times x minus 1 transpose v, right? So if this is my Lagrangian function, I would like to find the infimum over x. I've got a nice argument over here, so g of nu, which is the infimum of x on the function Lx nu. Got two nice cases. Imagine that my matrix W plus V is not PSD, not positive semi-definite. So what happens here? I can always find a vector x that could push this term downwards due to the negative eigenvalues of W plus V, right? So you can always scale your x to attain a lower term, x transpose W plus Vx, and hence this is unbounded below in x. However, if w plus v is positive semi-definite, you can just, pick your x to be the eigenvector corresponding to the minimum eigenvalue of w plus v. Hence, this term is lower bounded below by, in this case, I'm going to write a note here, the infimum with respect to x onto x transpose w plus v. X is just lambda min of w plus v, which is positive. That's important. Why? Because the infimum will turn out to be simply this term, which is minus 1 transpose times v. Simple as that. Okay? So, using the bound up here, we can say something about all three examples. So, in example 1, we can say that g of nu is the lower bound on the optimal solution, p star, of the least square problem. We can say that in case g of lambda nu exists, then in example 2, the LP problem, minus nu transpose times b is the lower bound on the optimal value of the problem. And in example 3, the two-way partitioning problem, we can say that if g nu exists, so when w plus v is positive semi-definite, then minus 1 transpose times nu is a lower bound on the optimal value of the two-way partitioning problem. Now there's one very important thing I'd like to tell you. Imagine the following problem. So imagine I'm trying to minimize a cost subject to x is equal to 0, right? What is the dual function here? So first of all, I'm going to write the Lagrangian Lx nu. There's no lambda because I don't have inequality constraints. It's equal to f0 of x plus mu x, right? We can extend this to be a vector, and this will be a transpose. And now if I look at g of nu, which is the dual function, it is the infimum over x, domain of the function, of Lx nu, right? Which is in turn the infimum of f0 of x plus mu transpose x, right? Now, let's write this as a supremum for just one moment. So I'll insert a minus right here. I'll say an infimum is minus a supremum, right, of x, and I'll insert a minus inside. So a minus of a minus with a supremum returns you to an infimum, right? It's as if you have this function, f of x, this is the infimum over here. Well, instead, I'm going to take minus the whole thing. So minus, I'll have this as such. So now, if this is the function h of x, for example, this is minus h of x. Instead of looking for the infimum, I'll look for the supremum. And the supremum happens to be the negation of the infimum. So that's why there's another minus over. Now, what is this function over here? If we go back to this section of the course, conjugate convex function, we can see that the supremum of y transpose x minus f of x, where the supremum is taken over x, is in fact the conjugate function of f of x. So here we've got the same form, actually. So organizing a bit of terms, I could write this as minus mu transpose times x minus f0 of x. So this is minus this conjugate function, which is f star, the conjugate of 0, but this time without a y transpose, I've got a minus y transpose, so it's minus mu, right? So for this problem right here, we see that the dual function is written in terms of the conjugate function of the cost. So we're going to name this section of the lecture relationship between the conjugate function and the dual function. Imagine I'm minimizing a cost subject to an inequality constraint and an equality or affine constraint. The Lagrangian of this problem, as we saw before, could be written as the following. Now, taking the dual, we've got the infimum of the Lagrangian with respect to x, right? Now, let's extract terms that do not depend on x, because we've got this term and this term that do not depend on x, so they do not take part of the infimum. That said, we can write the following, right? We can also collect terms that depend on x over here as such. Note that we can write this in a really similar way as here, we're going to flip the infimum to a supremum, that is, use the minus trick. So minus supremum of minus f0 of x plus, with a minus inside this term right here, so minus lambda transpose A minus mu transpose C x, lambda transpose B minus mu transpose D, right? And we're going to write this as a y transpose x. How do we do that? All you have to do is just do a transpose of a transpose. That is, flip those terms as such. A transpose lambda minus C transpose mu. So now this guy is a minus conjugate function of the cost of the following vector. That is minus A transpose lambda minus C transpose mu, right? With those constant terms. So really, this is your dual function expressed in terms of the conjugate function of the cost. Now, what is the domain right here? The domain of your dual? It is simply all pairs of lambda nu such that those terms right here belong to the domain of the conjugate function. Let's see some few examples on the dual function in terms of the conjugate function of the cost. So example number 4 is going to be equality constrained norm minimization. So here I've got to minimize the norm of x subject to an affine constraint, right? f0 of x is the norm of x. We've seen previously, you can actually derive the conjugate function of the norm using the supremum over x, y transpose x plus the norm. This is actually 0 if the so-called atomic norm, sorry, this is a function of y, my bad. The atomic norm of y is less than 1. We'll talk about the atomic norm later on in the course. But let's say you just derive the conjugate function of the cost, just this. You can easily express your dual without having to pass through the Lagrangian. So you can just, you've got those terms over here popping out from the right-hand sides of the inequality and equality constraints respectively. In this problem right here, I've only got equality constraints, so I've got the minus B transpose mu, that is only this term right here, and a minus f0 conjugate of minus A transpose mu. That comes from this term right here. Now you're going to tell me, oh, there's a lambda, but lambda here is linked with the inequality constraint. Right here, C, in my problem down here, C is playing the role of A because it's in the affine constraint, so it's a minus A transpose mu. So using the form of the conjugate function, this is, instead of a y, I've got a minus A transpose mu, so the argument is held on minus A transpose mu on the atomic norm of this guy being less than 1, and we're going to augment a minus B transpose mu minus 0, which is this guy, else we've got a minus infinity, not a plus infinity, due to the minus over here. Okay? Another really quick example is entropy maximization. So this is applied a lot in information theory, where you've got some uncertainty and you're trying to, maximize given or optimize in a worst case scenario. So minimize the entropy defined by probabilities in x, subject to, you're going to force that all your x's add up to 1, right? So that they report probabilities and some inequality constraint, right? This is easily written as 1 transpose x equal to 1, where your 1 transpose is a vector of all 1s, right? I'll write that in green. By the way, h0 of x is the entropy function. That is the sum of xi log xi. There's a minus, but there's a minimization, so it cancels that out. So over here, doing a bit of math, so if this is your f0 of x, then your conjugate function is in fact a sum of exponentials. yi minus 1. Got n such terms because x is of size n. So you can easily write your dual using this formula. It's minus f0 star of A transpose lambda minus C transpose nu. Just copying the formula. Minus lambda transpose D and the minus mu transpose B, right? Actually, this is the B goes here and the D goes here. My D is just the one scalar. So this, we've got only one nu. So it's a nu, size 1. Your C right here is a 1, and your A lambda is an AI transpose lambda, because it's decomposed as such. Finally, you're going to get a minus summation of exponentials as minus AI transpose lambda minus nu minus 1 minus lambda transpose B minus nu. This is your dual without having to pass through the Lagrangian. In this lecture, we've introduced the Lagrangian function of a general optimization problem. Then we introduced the Lagrangian duality, or the Lagrangian function in particular. Next, for each Lagrangian function, we defined a Lagrangian dual function. That is the infimum of the Lagrangian function with respect to x. We gave a lower bound on the optimal value of an optimization problem that always turns out to be the Lagrangian dual function, g. We gave an example on MATLAB to visualize or verify that this inequality is always true. So after that, we derived the Lagrangian function and its corresponding dual for 3 examples: the least squares, the linear programming in standard form, and the two-way partitioning problem. Next off, we saw a direct relation between the conjugate function of the cost and the dual function g, which is the one right here. So given an optimization problem, not necessarily convex, with inequality and equality constraints that are affine, of course, the relationship between the dual and the conjugate function of the cost turns out to be the following. We gave 2 examples on that to derive the dual, as we saw right here, without having to pass through the Lagrangian function. The first example was equality constraint norm minimization, and the second one was entropy maximization. I hope you enjoyed this lecture. I hope you found it beneficial. To help me continue with this channel, please consider subscribing to this channel, sharing it on social media, liking the video, and in case you have any questions, do not hesitate to comment down below in the comments section. Thank you so much for watching this video, and I'll be seeing you in future lectures. Thank you so much, and I'll see you then.